Hi everyone and welcome to the second Unity lesson for .NET Professionals. Today we will continue investigating computer graphics and we will talk about Unity shaders. As been said in previous lesson, graphics pipeline has vertex and fragment shading stages. Unity provides an API to program these stages and control what's happening there. Unity uses several kinds of shader programs. They are shader lab, surface shaders, and vertex fragment shaders. The last one is the closest to pure CG shaders and provides more control. Also, they are pretty low level, so let's start with them. First, what you see in any Unity shader is some shader lab code that describes shader properties. Let's refer to one of built-in Unity shaders, unlit/transparent. The first thing is shader name, which is used to differ this one from others and be able to select it in Material Editor. Next comes properties block, which exposes some variables in Material Editor. Then you can see subshader block. When targeting different hardware, it makes sense to create different versions of shader to support them all. After that, the path block. Sometimes the visual of the art are so complex that it has to be rendered several times with different setup. For example, to make shader work with shadows. Each path has some text, which describe how to use this path. For transparent shader, the blending algorithm has to be specified. For more information, please refer to Unity shader reference. As you remember, vertex data has to be passed to GPU for transformations. In this method, two structures are used. First structure, update_t, is used to pass vertex data to vertex shading stage. In this shader, it contains vertex position, UV coordinate, and some ID for GPU instancing. This structure describes the vertex and is passed to vertex function. Here we make vertex transform from local to camera space and make adjustments to UVs in order to take into account scale and offset of main texture that has been set in Material Inspector. This function is called for each vertex simultaneously. Notice the variables, which names are the same as in properties block. They are used to read the data from material properties. Also, if we look at a vertex color shader, you won't see any update structure. The reason is that we use update_full structure, which is defined in unitycg.cginc. You can find its source in Unity installation folder and see that it contains almost all possible vertex data. Another structure is called v2f and is used to transfer transformed and interpolated vertex data to fragment function. So it has similar set of variables. It is filled in vertex function and then passed to fragment. The fragment function is called for every fragment or screen pixel. It samples a texture at specified UVs and returns a calculated value of the color. That's why you want to place as much calculations as possible in vertex shader in terms of optimization. Also, the precision of such calculations are much lower due to interpolation. Don't forget about that too. Another type of Unity shaders is surface shaders, and they compare to vertex fragment shaders just like C# compares to C. They are more high level, and a lot of stuff is done without your help. All you have to do is describe the parameters of the surface. That's why they are called surface shaders. Let's have a look at this diffuse shader. It implements diffuse shading model, as you could understand from its title. It looks pretty similar. You can see the same shader lab blocks. But the diversity comes when you look at CG program block. As you can see, it says surface surf Lambert. What it means is that we have a surface function named surf, inside of which we describe the behavior of the surface, the material we're implementing. This function, similar to frag, is called once for fragment. Lambert means that we are using Lambertian lighting model. For example, it could be blend phone instead, which is used for glossy surfaces. Actually, the code for lighting calculations can be found inside lighting.cginc file. So all we have to do is to fill surface output structure inside surf function. This structure is also defined inside lighting.cginc file. You can see which fields it has. Albedo is diffuse color of the surface. Normal direction at the point. It can be read from normal map or just read from vertex data. Emission is additive color for surfaces that emit light themselves. Specular is amount of surface specularity is used in blink phone model, same as gloss, which defines how blink of light looks. Alpha means opacity, so with alpha set to 0, your mesh will be transparent. Note that in order to make transparent material, you have to do two things. First, add alpha directive after pragma surface surf Lambert. The second is define the blending algorithm the way your surface interacts with surfaces underneath. So, writing surface shaders are much simpler. Anyway, as soon as you can't control the amount of different calculations being done, in some cases they can be less performant. Also, you have a little less control in how your surface is lit. The last type of shaders, shader lab. And they compare to surface shaders just like C# versus, Playmaker or Unreal Blueprints. It has been made, as I think, to simplify shader coding for beginners. Anyway, they were too hard for me to understand really, and since I had surface shader, I could find no reason to use Unity's Shader Lab shader. So don't ask me to explain their syntax. You can read this article from Shader Reference if you want. Well, let's make some experiments and see how it works. First, let's add some change in value to the resulting vertex position vector. For example, a sinus value of current time variable, which was kindly provided to our shader by Unity Technologies. Saving the shader, go to Unity, and you can see how our mesh begins to bounce at literally no CPU cost. Let's continue our experiments and add some texture scroll to our shader. For that purpose, we will add time value to UV coordinates. Note that when entering frag function, we always get fresh value of UV, so all changes we do here are dismissed in next call. That's why we have to add new time value, not just increment UV. Again, saving shader, and voila, nice scrolling effect. Let me now show you how we pass custom values from vertex to fragment function. First, we'll add our custom field to V2F structure. Usually, they are passed as text coord with a number. It is usually float 4 vector, but could be smaller. Numbers 0 and 1 could be taken by main UV and secondary, for example, lightmap UV. So check if something weird happens. We'll use this field for transferring colors. In vertex shader, we'll fill this vector with some values. Let's use fractional portion of my favorite time variable. By the way, it's a vector. It contains values that change with different speeds. So we'll have some randomness. Time.xyzx. Note how we can use these postfixes. In this case, a new vector will be generated by compiler. In order to visualize what we got here, we will multiply texture color by this value, so the texture will be colorized. What you can see here is the most popular way of debugging shaders, displaying vectors on the mesh as colors. One last thing I wanted to mention is that if you want to see the lowest level code that your shaders are compiled into, you can check Shader Inspector in Unity, and there is a button, Compile and Show Code. Along with it, you can find drop-down button where you can customize a set of platforms your shader will be compiled into. This lesson won't answer all the questions that you face when trying to create an effect or develop a new material. Anyway, it can be a good start point for your experiments, which will help you understand how shaders work and what you can do with their help. That's how I learned them, by discovering other shaders code and experimenting with my own ones. So thank you for your attention. Leave your questions in comments section, subscribe to my channel, click the bell icon, and see you in the next lessons.